Welcome to the second lecture of Analog Integrated Circuits Design. In the yesterday's class, we discussed on models for analog design, and we just discussed a few things about MOSFET. All right, so we'll be continuing the discussion, and today we will see the models what we use for design, analog design. Okay. So before starting, I would like to start by discussing about this. Uh, the various components which are available on an integrated circuit. So what are the various components available on an integrated circuit? So can you guys respond in the chat box? What all components will be available on an IC based on your understanding? Now, typically on an IC, on an integrated circuit, what are all components? When I say components, you can think those components as devices also. Yeah, transistors, very good. Yes, you'll definitely have transistors. And for our course, as I mentioned, I'll write it as MOSFETs because, yeah, definitely many circuits will utilize even BJTs. Yes, Avinash, resistors, diodes, capacitors. All right, very good. Resistors, capacitors. Then what else? Yeah, I saw diodes. Any more answers for that? Apart from resistors, capacitors, what else will you see? Definitely, you can see even inductors also these days, right? So why specifically I have written only these components starting from transistors, resistors, capacitors, and inductors is just to give you one classification or one way to understand different types of ICs. So what I meant by that is um, when you look at a digital IC, so when I say a digital IC, probably you will remember what you have learned in your ADDC course in your last semester. Say, for example, when I say digital function, it will be almost all the time. Mm, what we are expecting the result will be either 1 or 0. Whatever function you have, we are trying to realize using realizing we want to get your output as either 1 or 0, and that is possible if you use transistors or if you use MOSFETs. It is very apt, and it is very easy to actually get such kind of response of ones and zeros. Or in general, what I can say, digital ICs, majority in the most of the cases, digital ICs will only have MOSFETs, or it only have transistors, or with only transistors we can realize any digital function. And so if it is only transistors, then we can say it as a digital IC. I hope I'm clarifying things. Now, when you come to analog integrated circuits, or the course, whatever course is about analog IC design, when you come to analog IC, apart from MOSFETs, you will see few more components. One component what you will see along with MOSFET is sometimes you will see resistors also, because most of the time even resistors will be replaced using MOSFETs in ICs, but in certain cases we will use resistors. All right. So if you see resistor components, in certain cases we will definitely use some diodes for some applications. So when you see resistors along with MOSFET, most likely the function realized by the integrated circuit will be analog in nature. Now, along with this MOSFETs, resistors, if you have capacitors. If I add capacitors to this now, let me tell you why do we need capacitors. Can I get a response in the chat box? What is the role of a capacitor, or why do you need capacitors in circuits? Why do you need capacitors in an integrated circuit? Can I get some response? Why do we need capacitors? Yeah, to store energy, to store charge. Yes. So basically, whenever you need to store a value or store a signal, we use capacitors. And such functions, or okay, let us think, when do you need to store a charge or store a value? In most of the cases, we store a value. Um, if you have an analog signal, basically analog signals can be stored in a capacitor. So we store this analog signal in a capacitor, and then we will convert that into digital. That is the basic purpose of a capacitor. Or when you use capacitors along with MOSFETs and resistors, we call such ICs as mixed signal IC. So why I call it as mixed signal IC is because it is that the function realized by that IC, the main idea is to convert an analog signal into digital. So it will store the value in an analog signal, and it will convert that into digital. So that is why we call it as a mixed signal IC. Mixed signal IC means it contains both analog as well as digital signals. Now coming to the last, adding the last element. Along with all these things, if we add inductors to this, we call the function realized by that IC as RFIC, or radio frequency integrated circuit. So when I talk about radio frequency integrated circuits, which are circuits which works at high frequency, we definitely, in most of the cases, we use inductors, right? So based on the components available on an IC, this is how we classify. So when I say classification, this is not the not a very strict way of classifying things, but this is just to understand or to differentiate that there are different functions implemented on an IC. It can be digital, it can be analog, it can be a combination of analog and digital, we call it as mixed signal, or it can be something called as radio frequency IC also. All right, I hope I clarified that. If you have queries, please put in the chat box. All right, so taking forward from yesterday's discussion, yesterday we spoke about enhancement type MOSFET, enhancement type MOSFET, and for the example, I'm taking N MOSFET in that. And you are familiar with MOSFET as a 3-terminal device, but now I am considering, or I am just taking the 4-terminal MOSFET, and the terminals are, this is gate, this is drain, source, and this is body, right? And now for this MOSFET, we are always interested in the current flowing in the MOSFET, right? So when I talk about current in a MOSFET, yeah. So when I talk about current in a MOSFET, uh, can you tell me the current? All right. So can you tell me how can I write, or this current in this MOSFET is a function of which all variables? Whether my question is clear? So in this MOSFET, we will apply this voltage. This is VGS. Now between drain and source, we'll apply another voltage. We call it as VDS. And from yesterday's discussion, I told you that we'll apply one more voltage, that is between source and body, where body is kept at the same or even at a lower potential. In that way, um, we call it as VSB. So what I mentioned yesterday is body should be connected to the least potential in the case of an N MOSFET, or it should be at the same potential of that of source. So whatever I have marked here as VSB can be 0 or it can be positive. VSB can be positive. So in that case, how can I write ID? So can you tell me ID, how to write ID, express ID as function of which all variables? Are you guys responding? So a drain current will flow. Yes, yes, Sri Harsha. It is a function of VDS. It is a function of VGS, but not directly VT. Why? Because VT, it is not directly depending on VT. Rather, it is depending on the terminal voltages itself. So I can write ID as function of the terminal voltages. One is VGS, another one is VDS, and another one is VSB. This is how generally how I can write ID. So in your last semester, when you were discussing AMC, you would have seen the dependency of ID on only these two voltages. Now we are bringing the last terminal also into picture, so we need to consider this additional voltage, which is VSB. All right. Now, as yesterday, I'll quickly list down the regions. This we have discussed yesterday anyway. Regions of operation. We know that the first region is cutoff, where your current is equal to 0 and your VGS voltage is not sufficient enough to turn on the device. And the second region is called as linear, where you are applying a VGS which is greater than or equal to VT, that result in a current and whose value can be written as mu and Cox W by L into VGS minus VT into VDS minus VDS square by 2. Right. Now one more condition we need to talk here, which is the VDS condition. It should be less than or equal to VGS minus VT in order to maintain in linear region of operation. Right. Now coming to the third region, we call it as saturation region, where the first condition remains same, and we should also have VDS greater than VGS minus VT. That will result in a current which can be written as half mu and Cox W by L VGS minus VT the whole square. Right. So these are the three regions and the corresponding current. Now, if you look at the characteristics, so immediately by looking at these three regions, we can say that in cutoff region there is no current. So what is the application? We will see that in linear region. You can see that the name itself is called as linear because the current is proportional to the applied voltage. So linear region, otherwise we call it as a resistive region or ohmic region or triode region. These are the other names for the same region. Now in saturation, we know that current remains constant, and here it will act as a constant current source. These things you have already studied, and I'm just recollecting or reviewing those things. This acts as a constant current source, right? Uh, any doubts or any more things you want to discuss on all this? Now when I talked about digital IC, what happens is all digital functions, when we realize as ones or zeros, MOSFETs will be switched between these two regions. Either it will be off or it will be on. When it is on, it should provide zero resistance. When it is off, it should provide very high resistance. That is what happens in a switch. And when we realize digital functions, what we need is exactly switches. So transistors will be operated between cutoff and linear to realize switches. This is where we use, or for our course, we are interested to operate And when we consider some non-idealities, we know that even that current will slightly vary. That is what we call it as channel length modulation. Right. But in none of these regions or none of these regions, we talk about the voltage VSB that we have to bring in now. All right. So let us start. Okay. Now, one more clarity I want to give you guys here, which is about models. When I say models for analog design, we are developing or we are using only models. Can you guys tell me which region of so when we talk about models or when we talk about the small signal models, uh, are we drawing models for a specific region or it is models common for all the three regions? What is your understanding on that? What is your understanding on that? It is in saturation. Yes, that is true. Yeah. It is for saturation region. So whenever we talk about models, small signal models, we are referring to, or by default we assume that transistor is in saturation region. So there are implications for this point. So when we say transistors are in saturation, the meaning is the transistors or the circuit is already biased. Already biased. What is the meaning of that? Suitable voltages are given. When I say suitable voltages, a proper VGS and VDS are given, already biased, are given such that this condition, these two conditions are maintained in that. All right. So when we you would have observed in your AMC course that in small signal model we always say that DC are 0 or DC are you would have grounded the DC voltages, right? So that is for the ease of analysis. In reality, voltages are already there. Based on the voltage, the transistor is in saturation region. So once it is in saturation, then you can consider only the small signals. Yeah, I am coming to that. Right. Now, so when I say model, we are drawing or we are discussing the models where transistors are assumed to be in saturation. For all the models, we assume that transistors are in saturation region. Now, probably I asked this question yesterday also. Why do we need a model? Or what we exactly do by drawing a model for MOSFET? Any answers for that? Are you guys with me? Can I get response in the chat box? Not for this question, in general. Are you guys with me? Am I going very fast? All right. So, yeah, majority response are from the same people. What about others? I can see 36 students here. Okay. So, when I say model, what we do here is we are representing. We try to represent MOSFET. MOSFET model means we represent MOSFET in terms of known elements. What is the meaning of known elements? Representing MOSFET in terms of known elements. All right. Yeah, thank you for that. So what is the meaning of representing in terms of known elements? What are the known elements? So what are the elements through which we can use and study, or which we can represent the MOSFET? Okay, let me start with this. Let me start with a resistor. All right. So I have a resistor here. which is carrying a current I. The voltage across the resistor is V and the resistor value is R. So how do you represent the IV character of this resistor? How will you represent the IV characteristics of this resistor? So usually by practice on x-axis we will take V and y-axis is I, and we know that in a resistor the current is proportional to the voltage. So if that is the case, you have a straight line, and the slope of the straight line we call it as, slope is nothing but so what is slope? Slope is dy by dx. So dy by dx means it is change in current with respect to change in voltage. The inverse of that is what we call it as the resistance value, right? So this is the IV characteristics of a resistor. So this is a known element. Known element sense we know the we really know the response, or we really know the characteristics of a resistor. Now, similarly, can you try drawing the characteristic of voltage source? Characteristics of a voltage source. How a voltage source cara will look like? I will consider that this is the voltage source. The current through the voltage source is I, and this the value is V naught, the constant voltage. This is marked as V. So how will you draw the characteristics of this? Can one of you switch on your video and can you show me the characteristics of a voltage source? All right, I'm not able to see. Yes, I hope I'm seeing the resistor one, not the voltage source.
The bottom
Very,
also.
very good, very good, very good. True. Who's that? Sri Harsha. Thank you, Sri Harsha, for that. So a voltage source, we know that the voltage across the voltage source remains same. So voltage value here is given as V naught for any current. This is the response of a voltage source, right? This is the response. Now, similarly, if you try for a current source, how do you draw the response of a current source? Say this is current source, say constant current I naught. The current flowing is I naught, and this is the voltage V. If you draw the IV characteristics, so why am I drawing all these things? Because I said that when we say model for a MOSFET, we are trying to represent MOSFET in terms of known elements. And what are the known elements? The elements which we know the characteristics. The IV characteristics of known elements are like resistor. We know the cara. When I say a voltage source, we know what is a cara. When we say current source, what is the cara of a current source? As similar to voltage source, the current across a current source, current through a current source will remain same irrespective of the voltage. So here the current value is I naught, and this is the cara of a current source. All right. So since you have done all this, let me ask you to draw a combination here. So you have a current source which is having a value of I naught, and you have a resistor which is connected in parallel. So you have a voltage V across this, and this is current. Now that current is divided into two. One is I naught current, which is through the current source, and you have another current here, which can be marked as IR, which is a resistance, which is a current through the resistance. Now in this case, can you tell me what will be the cara? So again, why am I doing this? Because I told that we are trying to represent MOSFET in terms of known elements, and I'm trying to combine two elements and observe the cara of that. All right. What we can do is the IV cara again. This is V and this is I. When you draw the IV characteristics of this, The current through the current source will remain same, so it is same as I naught, right? The current through the resistor will be always linear, so you will see a response something like this. Let me use a different color for that. So this is for resistance and this is for current source. Now when you have a combination, you will almost see that your response, the combined response for this will be something like this. It will start somewhere over here and it will be changing something like this. Yeah, not exactly, yeah, but similar to this. All right, will you agree to that? There is a current source and a resistance, both are connected in parallel. The current source cara will remain same, the current will not change. The cara of a resistance is also same, it is proposed, it is linear. Now when you have both, it will be almost adding up, it will be adding up and it will have a response which is shown as in the blue line there, right? So we will see this kind of response when you understand MOSFET, or now itself you can relate this to the MOSFET cara. MOSFET in a practical MOSFET in saturation will have this kind of cara. That is why you can definitely see or you will see the small signal model of a MOSFET with a current source in parallel to a resistance. We are actually coming to that. Yeah, I'm just telling you in prior. Any questions so far? Any questions?
Sir,
Yes.
is isn't that voltage source with a series resistor?
Which one?
Like, can't we convert that current source into a voltage source?
Okay. When you
So
convert this current, so yeah, come
yeah,
again.
will that changing of current source to voltage source affect the graph?
Uh, okay, so you are asking me, now you have a current source in parallel to a resistance, and you are applying some transformation, and you are trying to convert that current source in parallel to a resistance to a voltage source in series with a resistance, isn't it?
Yes, sir. Yes, sir.
Okay, so when you do that, yeah, then your response will not look like this. Yes, your response will not be like this because you have a voltage source and there is a series resistance. Your response will be a little different, not little different. It is quite different from this. Yes,
Okay, sir.
Akash. Yeah. So I didn't get. Why did you ask that question? You want to relate something here, or
I was just asking the doubt, sir, because there
uh,
was a series resistance. That's it.
all right, all right. Okay, okay, yeah. So why? Okay, now to clarify, why I have taken only this combination of current source in parallel to a resistance is just to relate this with your MOSFET characteristics. All right. I hope Akash, you are clarified, or if you have doubts, you can still ask me.
Clarified, sir. Thank you.
All right. Yeah. So now, probably the initial classes, maybe today and even tomorrow, whatever we discuss, if you feel that you already know that, you can just ping me in the chat box. Because I just want to brush up these things because this clarity will actually will make you comfortable when you go ahead with the analysis, the further analysis. All right. So as I mentioned in the beginning, the drain current of a MOSFET depends on three variables. One is VGS, another one is VDS, and another one is VSB. Now here the idea of developing a MOSFET model, the small signal model, which is familiar to you, is actually to understand the influence of these three voltages on current and coming up with a model in terms of known elements like a current source or a resistor or a voltage source, something like that. So let me start the study by writing the variation of ID with respect to VGS. That is the first thing what we do, the variation of ID with respect to VGS. To understand that, again, I am just drawing a MOSFET here. I am drawing a MOSFET. Now for that, we know, as I mentioned before, we should apply suitable VDS and VGS. Now I should apply a VDS here. This is VDS. there should be VGS also. So when you apply both VGS and VDS, what I can expect here is, so what I applied here are DC voltages. Now when you apply DC voltages, you can expect a DC current here, and I'm marking it with this yellow color ID. All right. So for the time being, I'm not mentioning or marking something on the body, but sequentially, I will even consider body terminal. Okay. Now with the DC voltages, you have this DC current that we know, and even when we try to develop the model, we assume that saturation region will be maintained by suitable voltages. That is what this VGS and VGS does. Now we want to know how this ID varies with respect to VGS, or we are interested to know um, how this drain current vary when there is a change, when there is a small change in VGS voltage. So I am bringing in one term here, something called as small signal. As I mentioned in yesterday's class, all the real world signals are analog, and they are quite weak, or their strength is very less, in the range of microvolt or millivolt, especially the physiological signals or even the voice signal. We call such signals as small signals, and we use amplifiers to amplify such small signals. Now we are trying to understand MOSFET as an amplifier to amplify such weak signals. Now when I bring in MOSFET, so when I bring in MOSFET to amplify such a weak or a small signal, now I am trying to understand how a MOSFET respond to such variations, right? uh, am I making my statements clear? Can I get some response?
Yes, sir.
Yeah, maybe others also can respond in the chat box. All right, okay. So I'll quickly wind up this. So what I will do here is, in order to understand the effect of that, I am actually adding a small varying signal here, and I mark this as VGS, because I want to know how a MOSFET respond when there is a change in VGS voltage, right? So this can be identified as a DC voltage, and whatever I have written here as small VGS can be understood as an AC voltage or a small signal voltage. All right. Now, see, for a DC voltage, if there is a DC current, whenever there is an AC voltage, you should expect an AC current also. Now, I mark that current as small id. All right. Now, if you look at the gate, you can see an AC voltage on a DC voltage. Or if you mark the entire voltage here as plus minus, it is a combination of, this is a composite signal of both AC and DC. Or I can write this as small v capital GS. This is what we call it as a composite signal, where it is a combination of small VGS, which is AC, and capital VGS, which is DC. And corresponding to this, I am at the drain current, I am getting a DC current as well as a small signal current. So I can write this as small I capital D, which is a composite current, which is a combination of small id and capital ID. I hope you are able to relate this, the small signal current and the DC current. So DC current is always there, but here I am explicitly writing it. But in most of the cases, once we do DC analysis, then from there we will take all the small signal parameters and we'll do only with small signal analysis. We'll proceed only with small signal parameters. All right. Now, if that is the case, what I'm trying to do here is I'm trying to understand the variation of ID with respect to VGS. So I will write what is ID. What is ID? How can I write ID? ID can be written as half mu n Cox W by L into V capital GS minus VT the whole square. Now you will wonder why only this expression. As I mentioned, we are studying the model of MOSFET in saturation. That is why I have taken only this expression. Now what is this VGS? This VGS is a composite signal which I have marked as small VGS plus capital VGS. Right. Now when I write this in detail, I can write it as half mu n Cox W by L in brackets small VGS will be replaced as, sorry, this composite signal will be replaced as this, and this can be further analyzed. So when I analyze this further, what I will do here is I will just separate the constant voltages and the AC voltage. So I will write it as it is now, like this, and I will assume that, or I will consider that this is say this is A and this is B, and now this is in the form of A plus B the whole square. That will definitely give you some result, and if I write that, I can write it as half mu n Cox W by L VGS minus VT the whole square plus this is A square, and then next is 2AB terms, so 2 into half, it is 1, so you will get it as mu n Cox W by L into VGS minus VT into small VGS. This is the second term, and you will have a third term where it is half mu n Cox W by L into VGS square. So what is on left hand side? It is capital, sorry, small I capital A, which is a composite signal. All right. Now, if you look at the right hand side, you have three terms, and can you identify all the three terms? What is the first term? What is first term? Half mu n Cox W by L VGS minus VT the whole square. Yeah, it is the DC current. Very good. So this is ID. Now, what is the second term? Okay, before talking about second term, if you look at the third term, you can see that it is half mu n Cox W by L VGS square. Right. Now, what is this VGS? This VGS is a small signal of the range of milli or micro. So the square of it is still smaller. So in that case, or for all analog applications, we can just neglect this. We can just neglect that term. We are neglecting it. I'm not simply neglecting. I'm neglecting because the contribution of that term is very, very small. Now, if you ask me what is actually that term will actually give you something called as harmonics. You will get harmonic current from those terms. So such details we will study little later in your course called RFIC design. We will bring in the effect of nonlinearity, which is giving you this harmonics. Now, leaving that term, I can write the first term as the DC drain current. What about the second term? Looks like the second term is the, as per our discussion before, the second term should be the current, which is the result of your small signal voltage. So I will write this as small ID. Now, what is the small ID? Small ID is equal to mu n Cox W by L into VGS minus VT into small v capital GS. All right. Now, this is the relation between small ID and small VGS, or the small signal current and small signal voltage. And we call this term, the mu n Cox W by L term, as yeah. So that term is called as, I'm just writing the expression again. Where this term is called as transconductance or GM. That means I can relate small signal current to the small signal voltage by this term small GM. Right. That is why we call this as the first small signal parameter. In AMC, you would have solved many problems to calculate small signal parameters, and this is the main one of the small signal parameter. All right. Now, how do we understand this graphically from the characteristics? So we have taken the relationship between ID and VGS. That means if you look at this at the characteristics, on the characteristics, we know that the graph is something like this. This is ID. This is not this ID. I should write this as I capital D. This is VGS. All right. Now, look at this. So I am looking at the characteristics of ID and VGS. That is what I have drawn here. This is the chara of a MOSFET, the relationship between ID and VGS. Now, x-axis is a combination of DC and AC. That means always this AC voltage is on, or always this AC voltage is sitting on a DC voltage. Or I will mark something like this. There is a DC VGS, which we call it as DC operating point, and on that DC operating point, if there is a small signal voltage, that is what you see here. The same thing here also. Let me use the other color just to correlate. Capital VGS is here blue. This is the DC voltage, and on the DC voltage, you are applying a small VGS, which is AC voltage. Can you guys hear me? Hello.
Yes, sir.
All right. Yeah. Okay. So let me finish this. Now, when you apply a small signal voltage on a DC voltage, what happens? I will try to map it on the same graph. This is a variation here. Now, for this DC VGS, there will be definitely a DC current also. So you can see that for the DC VGS, there is a DC current. This is the DC current value. Now, when there is a change in the voltage, the same change will reflect, not the same change, but the change will be reflected even in the current, and I can mark it as, right, how I will mark, I will actually map this to this point and even to this point, and from there I will be marking it to this axis, and the change in current can be marked as this. So this is the DC current, and on that you have AC current. I hope you guys understood this. So what is basically this transconductance? Transconductance is the figure of merit, or transconductance is basically the conversion, or what I can say is, if you take the slope of this, I can write it as the change in ID. The change in ID, I will write it as dou ID divided by change in VGS as this around an operating point. So this is happening not somewhere, it is happening at a constant VGS. Around an operating point VGS will give you the transconductance value Gm. Is that clear? Now you will be wondering why I have used this partial derivative here. Yes, I can use only partial derivative because drain current is not depending only on VGS, because it is depending on multiple. There are three more other variables to which drain current is depending. That is why I have taken partial derivative here. Is this clear? Now this will give you the first or the primary model of MOSFET. How will we write that? Conventionally, we mark it as gate. We mark this as gate, this side as drain, and this side as source. Three terminals. Now between gate and source, if you apply a voltage, which voltage? Small signal voltage, VGS, that will result in a current. What is the current value? Current value is ID, that is equal to small gm into VGS. This is your primary model of the MOSFET, or we call this model as ideal MOSFET model. Any questions on this? Any questions? Now what I will do here is I will so I wanted to do show a simulation of the MOSFET characteristics, but I do not the simulator, there is an issue. So I'm just I have the simulation result right here. So what you are seeing on the screen is the ID VGS graph of a MOSFET. So this is ID and this is VGS. And what you are seeing is as the red is the MOSFET curve. Now what I have done here is I have taken 2 points. I don't know whether it is visible for you guys. I have taken this point as A and this point as B, and the corresponding voltage and current is marked there. So the idea is just to measure this slope, which will give you the GM value. GM is delta ID by delta VGS, right? So if I calculate, maybe if you can see, you can calculate. At point A, the voltage is 420 milli and the current is 2.18 micro. At point B, voltage is 595 milli and the current is 40 micro. So when you do dy by dx, you will get GM. And if you calculate that, you may get close around 218 microampere per volt. Approximately. So this is ID versus VGS characteristics. So generally we write this ID VGS. Why I have changed it into small I capital D and small v capital GSCs is to say that now on a DC, so we are interested to know, we are actually interested to know about the change in current when there is a change in voltage. That is the main idea. So I hope this is clear, and if you have doubts you can ask, otherwise we'll continue on the next class.